Hello everyone, my name is Likit. The topic assigned to me is multiplexers. So let us see what is a multiplexer. A multiplexer, abbreviated as a data selector or MUX, as a group of data inputs and a group of control inputs. The control inputs are used to select one of the data inputs and connect it to the output terminal. The IC used to realize a multiplexer circuit is IC 74151. The 74151 is a high-speed digital multiplexer with 8 input. The IC provides the ability to select one bit of data from up to 8 bits of data in a single IC package. We have seen the IC 74151 in our laboratory. We used it to realize the 8:1 mux. The following figure, as you can see, shows a block diagram of a 2:1 mux. Here, I0 and I1 are the control input. I'm sorry, I0 and I1 are the data lines. A is the control input and Z is the output. When A is 0, I0 will be active and the output shows the 0. When A is 1, I1 is active and the output shows 1. As you can see, the equation of a 2:1 mux can be written as Z is equal to A bar I0 plus A I1. Yes, this is what I explained in the previous slide. It also acts as a switch by selecting the particular inputs as we saw in the previous slide. The internal diagram of a 2:1 multiplexer is displayed. The inputs are the AND gates and the output is an OR gate. For several other multiplexers, the OR gate can be a bubble to make an OR gate. This will make it an active low output. If it is not bubble, it is an active high output. Here is a multi examples of several multiplexers. The first one is a 4:1 multiplexer with 2 control inputs and 4 data inputs. The second one is an 8:1 mux with 3 control inputs and 8 data lines. And here the general block diagram of a multiplexer can be represented as 2 power n is to 1, where n is the number of control inputs and 2 power n is the number of data lines. Multiplexer logic. A digital design usually begins with a truth table. The problem is to come up with a logic circuit that has the same truth table. We have two standard methods for implementing a truth table, that is the SOP and POS solution. The third method is the multiplexer solution. As we have, as we saw with the K-map and MEV methods, we used the method of POS and SOP solution where we mark the quads, pairs and octets and write the corresponding solution. Here, the multiplexer solution is a more easier solution than the K-map solution since it does not require to draw any K-map or any other K-map related diagrams. Here is a problem, example problem, how to realize a given expression using a 16:1 mux. Now we enter all the inputs first and we mark ones for the all the minterms mentioned in the problem. The others are represented as 0. Here in the IC, A, B, C, D are the control inputs and D0 to D15 are the data lines. Here, whosoever output is 1, 1 is connected to VCC, that is plus 5 volts. All the zeros, that is if we have got the low output, they are connected to the ground. Y is the output of the IC and 9 is the complement of the output which we have grounded. The complement of the output is not required for us. The same problem we have implemented using 8:1 mux as we have done in the laboratory experiment. We consider a pair of two outputs as one input. Here we have considered D as 0 1 combination, D bar as 1 0 combination, and 1 1 is written as 1 and 0 0 is written as 0. Pin number 7 is taken as the fourth input, that is D, and that the complement of D is given to the 0th pin in the diagram. All the ones are connected to VCC and all the zeros are connected to ground as I discussed before. Advantages. As I said, MUX does not require any K-maps and any simplification. It is directly writing the truth table and reducing the truth table by considering pairs and implementing it. The usage of number of wires can be decreased. It reduces the cost and complexity of the circuit. It can make transition It can make transmission circuit less complex and economical. The implementation of a number of combination circuits can be possible by using a multiplexer. Disadvantages: additional delays required within switching ports and input-output signals which propagate through the multiplexer. This means that there are more delays while the input and output during the input and output propagation. So this reduces little bit reduces the efficiency of the circuit. Switching ports can be handled by adding complexity of firmware. As we said, the switching ports there is a delay in the switching ports, but the only way to solve the delay is to make the circuit a more complex. The ports which can be utilized at the same time have limitations. Applications: communication system, telephone network, computer memory, transmission from a computer system of a satellite. Here, the main application is the communication system, which I'm going to discuss in the next slides. Telephone network also uses a multiplexer system. In the telephone network, various wires are connected to the base station. The base station receives only one signal, and there will be a demultiplexer at the base station, which transmits the signal to several telephone networks. In computer memory, there will be multiplexers in the processors, as we have discussed in the CO course. Communication system. There are two types of multiplexers, namely analog and digital. They are further divided into frequency division multiplexing and wavelength division multiplexing. Time division multiplexing comes under digital multiplexers. Okay, there are two main types of multiplexers, namely analog and digital multiplexers. They are further divided into frequency division multiplexing, wavelength division multiplexing, and time division multiplexing. Let's see the figure how they are divided. As we discussed, multiplexer are divided into two types, analog and digital. Under analog, we have frequency and wavelength division multiplexing. Digital has time division multiplexing. Time division is divided into asynchronous TDM and synchronous TDM. Analog multiplexing. The signals used in analog multiplexing techniques are analog in nature. The analog signals are multiplexed according to the frequency division or wavelength division. In the diagram displayed now, we use is an analog multiplexer, as you can see. Frequency division multiplexing. This is an analog multiplexing technique which uses various frequencies to combine streams of data for sending them on a communication medium as a single signal. We can see a traditional television transmitter. All the TV signals, all the TV signals are sent as an input to the multiplexer, and all the signals are channeled through a wire which is then connected to a demultiplexer, and it receives the data from the other end on the other televisions. Wavelength division multiplexing is an analog technique in which many data streams of different wavelengths are transmitted in the light of the spectrum. If wavelength increases, the frequency of the signal decreases. A prism which can turn different wavelengths into a single line can be used as the output of the multiplexer and input of the demultiplexer. As we see, the commonly used wavelength division multiplexing technique is an optical fiber. We have discussed all the features and working of optical fiber in our first sem, that is in the physics. Here we can see that the transmitters, there are four transmitters that are connected as an input to the multiplexer. The multiplexer output is connected as an input to the demultiplexer. The demultiplexer then sends the signal to the receiver end. Digital multiplexing. The term digital represents the discrete bytes of information. Hence, the available data is in the form of frames or packets which are discrete. Time division multiplexing. In time division multiplexing, the time frame is divided into slots. This technique is used to transmit a signal over a single communication channel by allotting one slot for each message. Time division multiplexing is classified into synchronous and asynchronous stadiums. This is the Representation of time division multiplexing. It is similar to analog, but it uses digital signals. Synchronous stadium. The input is connected to a frame. If there are n number of connections, then the frame is divided into n slots. One slot is allocated for each input line. In this technique, the sampling rate is common for all signals, and hence the same clock input is given. The mux allocates the same slot to each device at all times. Yeah, we can see three sources which are emitting signals, and these signals are connected as an input to the multiplexer. The multiplexer then divides the signals into cycles, which is then transmitted over a medium and received at the other end. Asynchronous TDM. The sampling rate is different for each of the signals, and a common clock is not required. If the allotted device for a time slot transmits nothing and sits idle, then a slot can be allotted to another device, unlike asynchronous TDM. This type of TDMs is used in asynchronous transfer mode networks. In the diagram displayed, we have a voice signal, data packets, and image signal, which are all connected as an input to the multiplexer. Then the output of the multiplexer um, emits radiation, which are the wasted bandwidth, which means that they are not useful to us. Then they are uh, collected by these specific wires. Then they are used as an asynchronous transfer mode network. Thank you.